Now we will discuss how coarse-grained soil are classified using the USCS. This system is essential in geotechnical engineering. Let's break down how the classification process works using this flow chart. The first step is to decide if the soil is coarse-grained or fine-grained. This depends on how the size of the particles. If more than 50% of the particles in the soils are larger than 0.075 mm, then we classify the soil as coarse-grained. For soil with more than 50 fine particles, we use a different flow chart. Only we know the soil is coarse-grained, the next step is to determine if the gravel or sand. This distinction is based on the particle size. If more than half of the particles are larger than 4.75 mm, the soil is classified as gravel and we assign the letter G as the first symbol in the classification. If most of the particles are smaller than 4.75 mm but still larger than 0.075 mm, then the soil is classified as sand and we use the letter R as the first symbol. After determining whether the soil is gravel or sand, we look at the fines content, specifically the amount of smaller particles like silt and clay that are present in the sample. If the fine content is less than 5%, we consider the soil to be clean gravel or sand. If the fine content is between 5% and 12%, it has enough fine to impact the classification, and we will add additional symbol based on the fine's properties. For soils with significant fines, we then look at the plasticity of fine. In the other word, how sticky or moldable the fines are when wet. This helps us decide between two options. If the fines are more clay, we classify them as plastic fine and use C as the second symbol. If the fines are more silt-like, which means they don't stick together as much when wet, we classify them as non-plastic and use M as the second symbol. Finally, we end up with combinations that represent different types of coarse-grained soils. This classification helps engineers predict how the soil will behave under different conditions. And that's how the Unified Soil Classification System flowchart helps us classify coarse-grained soil. This is one of the first analyses carried out in the laboratory to understand soil properties better. The grain size analysis is essential because it helps us determine the distribution of different particle size in a soil sample, which in turn tells us a lot about the soil's behavior and how it might perform in different applications. Now let's dive into how this analysis is done. Grain size analysis of soil is typically conducted in two stages, depending on the particle size we are dealing with. So the first one is the sieve analysis for the coarse-grained particles, and the second one is the hydrometry analysis for the fine-grained soil. I will more focus to sieve analysis for the coarse-grained because in my case, the soil that I use is coarse-grained particles. In sieve analysis, we determine the particle size distribution by passing a known weight of soil through a series of sieves. Each sieve has a specific mesh size or opening that allows only particles smaller than that size to pass through, while larger particles are retained on top. This gives us a way to separate and quantify the particles according to their size. To conduct the analysis, we weigh the amount of soil retained on each sieve, which tells us the distribution of different particle size in the sample. Larger particles like gravel and coarse sand are retained on the upper sieve, while finer particles like silt and clay may be found on the lower sieve or even pass through the pan. The image on the slide shows a typical stack of sieves used in this process, with labels indicating the size of each sieve. This setup allows engineers to classify the soil accurately based on particle size distribution, which is essential for determining the soil's suitability for construction and engineering applications.